All right, so in this video we're going to try to tackle again this idea of graphing tangent and where it comes from, and what are these asymptotes your professor's talking about, why do these asymptotes exist, and just overall the pattern and shape of the tangent function. So what I kind of have here is it's set up. Again, remember these graphs are all coming from this unit circle. So let's talk about this unit circle really quick with regards to tangent. So if we come back over here and we start thinking about this again, okay, so remember this is still 0 or 2 pi. This is pi over 2. This is pi, and this is this 3 pi over 2. All right, but we're going to talk about some other things as well. If you notice, I have this negative pi over 2 here, and that's the first thing I'm going to start to label. So as I go around the circle, generally speaking, we always start on the x-axis and we travel counterclockwise. Okay, so when I travel counterclockwise, up here you'll see that these are all positive. Well, I can travel clockwise if I want to, which means I could start at 0 and I could go in reverse. Well, if I go in reverse, what we need to know is that this is no longer 3 pi over 2 because we're talking about the length from our starting point of how far on the radius of the, or on the circumference of the circle we've traveled. So 3 pi over 2 is no longer 3 pi over 2. What we need to know is that this is going to be negative pi over 2. This will be the negative pi. This will be negative 3 pi over 2, and then the 0 becomes the negative 2 pi for essence. So this is going to come into play in a couple of seconds when I start talking about why is it that the period is from negative pi over 2 to pi over 2 in a second. So a couple of other things we need to talk about with tangent is very quickly. Tangent, when we graph this of y equals tangent x, what we need to understand here very quickly is that tangent is looking at the relationships of both sine and cosine. And what it's doing is it's taking how I talked about before in some other videos, that the sine function is really measuring a displacement of when I start traveling on the circle of what's my height from my starting point, right? What's the displacement of vertical displacement? And the cosine is talking about what's the horizontal displacement from the y-axis. So for this particular one, what we need to understand is that we're now going to be talking about tangent is a comparison. It's a ratio of sine's displacement to cosine's displacement. And what now has to happen and what we have to observe and we kind of look at here is, okay, is there any time when the displacement of sine and cosine are equivalent? And it just so happens to be that, yes, they are. And what we begin to notice is that some important values are these pi over 4. At pi over 4, okay, the displacement from the y-axis and the displacement from the x-axis are identical. So thinking about this geometrically wise, these two things are congruent. They are the same exact length. Well, if here to here is the same exact length, that means they have a relationship of 1 to 1. So pi over 4 is an important relationship for us to know simply because that's when we get the whole numbers. So if we think about the critical values for tangent, one of them to note, okay, is always our starting point, which is 0. Okay, we also have this pi over 4. All right. And the other thing we want to take a notice at is that what happens when we get to pi over 2? Well, pi over 2 generally for sine was a good number and for cosine was a good number. The problem now is that the displacement of sine from the x-axis on the unit circle is a distance of 1, but cosine, okay, we get this 1, so displacement of the sine at pi over 2 is 1. But cosine, remember, is a measurement of how far away you are from the y-axis. And here I have a displacement of 0. So this now creates a problem. So you now have a fraction with 0 in the denominator, and for years you've learned that that's undefined. So if I have an undefined value, it means that I can never have a point, okay? So if I'm thinking about ratio and tangent, I can never travel along the circle, and I can never actually touch the y-axis. So what happens with tangent is it becomes like jump rope. It just hops over it and then continues on. So it doesn't count that value. You can't have it, and that's where the vertical asymptote comes in. I can get really close. Okay, I can travel and get really, really close to pi over 2, but I can never obtain it. So when I have this function that gets graphed, we'll talk about that. But at pi over 4, okay, we have this relationship of 1 to 1. Why? Because we're both a distance. I'm a positive unit away, okay, displacement with sign. Positive, I'm to the right of the y-axis, all right? And I'm also positive for the x. So at 1, I have a 1 to 1. So tangent will always have a 1 to 1. So at pi over 4, the outcome is 1. At 0, now this is the opposite. 0, okay, sine has the displacement of 0 and cosine has the displacement of 1. But that's okay because 0 over 1 is 0, so we get 0 here. All right. Now the other one we got to talk about here is, okay, so if I hop over this, right, and I start now going here from pi over 2, and I start going this way, well, this point over here, okay, ends up becoming a little bit more, but it ends up being, if we follow it, it's this 3 pi over 4. All right, so what I have is that 3 pi over 4, though, okay, notice it's to the left displacement-wise, but it's still positive. So the outcome for tangent in this case is going to be -1 because now we're talking about sine versus cosine. So sine is +1, all right, but cosine is -1, right? So if we think about this, and that's not the actual number. It's actually square root of 2 over 2 and square root of 2 over 2. I'm just talking about in the sense of relationship of a 1 to 1. So root 2 over 2 to root 2 over 2 reduces to 1 to 1. So that's why I'm just using this 1 to 1 fraction, a little bit easier to understand. So what we have is that this value is -1. So at 3 pi over 4, all right, we're at -1. And we're going to follow this pattern that I have 0 here and then another halfway. Okay, so now down here, okay, two negative ratios. So this is -1 to -1 actually produces, even though it's on here in the circle, a -1 to a -1 is going to produce this +1. So what we have here is the actual beginning of where that tangent function curve looks like. So we get back to 3 pi over 2, and again, my cosine becomes 0. My sine's -1. Can't have that. It's undefined. So if I can't obtain that, we have that. So now, why does this go on forever? And it's simply because as I travel and I get closer to here, my distance is actually increasing, and the distance here is decreasing. So what I have for sine, okay, I have sine is getting larger, okay? So sine is getting larger as cosine gets smaller. And what we need to begin to notice here is that the outcome will actually be a higher value, and it will just keep getting higher and higher and higher. So for instance, if I had 4 over 2, the outcome is 2. Well, if I change this to get larger and this to get smaller, so I take this to 5 and I say that to 1, notice the outcome becomes higher. So I went from 2 to 5. So while I'm never getting here, it will always continue the outcome. As I approach it closer and closer, the outcome will always get higher, but we'll never actually obtain that value. So that's why we put the arrows on the end. It has everything to do with just this basic concept here. So here we kind of get the basic beginning of the tangent. But the question is why does tangent go from -pi over 2 to pi over 2? Well, it has everything to do with kind of, well, we don't want to start something out here at -pi over 2 and 3 pi over 2. So what we do is we kind of look at this and go, okay, could I have made this somewhere else? What we'll begin to notice as we travel along this circle, right, at negative, okay, or at whatever this value is, if I travel this way, which becomes -pi over 4, I get this same relationship, and we get this -1. So now what you see is I have this same image here that it is here. Hence why we kind of use the sine. The sine has a period that starts at -pi over 2 and goes to pi over 2, because this is kind of centered around the origin where it kind of begins. So that's kind of my theory of why we do it. I don't know if it's exactly right, but I hope it's something that makes sense. But the other reason you can think about this is I kind of think of this as a ping pong wall. So let's pretend I couldn't hop over it. Well, if I go to here, I'm going to get bounced back. So the only continuous interval that I have centered around my starting point is I can go from here to the pi over 2, or I can go from here to -3 pi over 2, but I can't stop. But if I continue on for this, okay, so how's this going to help me do anything from before. Well, what happens if I have something like that alters my period? What happens if I need to shrink my asymptotes? What if my asymptotes move much like they did for the sine? What happens if I shift it up? What happens if I change my outcome? These points were nice. They were 1. They were -1, right? Those are nice values. So let's talk about that very quickly based on the unit circle again. So off of this unit circle, what we kind of had is those nice values that were created, which are going to be 0, pi over 4, pi over 2, 0, this negative pi over 4, and negative pi over 2. Well, going back to geometry again, all right, if we take a look at these points right here, okay, the distance traveled from here to pi over 4 is equidistant from here to negative pi over 4. Well, pi over 4 just happens to be the halfway point between pi over 4 and pi over, or 0 and pi over 2. That's equidistant. So what we have again occurring is the same thing kind of before. We have those 4 equivalent intervals. So what we need to do is much like the sine, but we need to just make sure that we know that the tangent has a period that is a length of pi versus 2 pi. Cotangent's going to be the same thing. And we'll talk about just has a different starting value and placement. But it will have a period of pi. So tangent, okay, has a period of pi. And that's going to be important because we're going to follow suit pretty much the same way as we did before. So with all that little background stuff, let's go a little bit farther. But now you have the basic relationship of what the tangent is. So we have 5 basic critical values. So I call these my undefined values, my asymptotes on a graph. That's what we call them, vertical asymptotes. But then we also have the 4 intervals, okay, that are created from 0, pi over 4, and negative pi over 4. So these are kind of the numbers we want to think about when we deal with tangent. So when we think about a tangent, remember we're going to go, instead of using 3 pi over 2, we're going to use negative pi over 2. And then we're going to start bouncing back. So we're going to go negative pi over 4, 0, pi over 4, and pi over 2. And I'm going to note very quickly just what the outcomes of tangent are. At negative pi over 2, it's undefined. Negative pi over 4, it's that 1-to-1 ratio. So the outcome is -1. At 0, the outcome is 0. Pi over 4, the outcome is 1. And at pi over 2, the outcome again is undefined, which is where your vertical asymptotes come into play. So let's, keeping this in mind, let's go ahead and make an example of what happens if I change some things. So instead of just being the tangent function, okay, the question came in to make it a little bit different. And it wanted to look, wanted to look a little something like this. So -1/2 tangent of 2x. So a couple things we have to remember. Same stuff kind of means pretty much the same as sine, and I like to just think, I like to call them critical values. But we have to come up with basically tangent, okay, again, tangent only wants to take the values of, say, negative pi over 2, negative pi over 4, 0, pi over 4, and pi over 2. Well, if I'm multiplying those by 2, okay, so essentially what's going to happen is that now I'm taking double them. Well, I'm essentially saying, okay, what number times 2 will give me negative pi over 2, will give me negative pi over 4, will give me 0. Well, that one's easy, right? Will give me pi over 4, will give me pi over 2. But I don't even really need to go that far. What I need to do is figure out what is my beginning vertical asymptote. And from there, I know that the original period went by pi, had a distance of pi. This is the value that alters the period, so the coefficient of the inside of the function. So I take this value and I cut it in half. Why am I cutting it in half? Because I want it to go twice as quick, which means I want it to happen in half the time. So I can either multiply by the reciprocal of this value, or I can divide by this value to figure out what the new period length will be. So the first things first that I want to do is I want to figure out my starting point. Well, the original starting point was at negative pi over 2. So I'm just going to say, OK, well, negative pi over 2 was the original. OK, that's the original asymptote. And we talked about why it's the asymptote. So I just want to use that. So I use 2x. So again, I'm not a fan of division. So I'm going to use the multiplication by a half. Multiplication by a half. And I get negative pi over 4 equals x. So my new vertical asymptote, my beginning vertical asymptote, right now I can come up here, I can go to negative pi over 4, and I can draw a vertical asymptote in. There it is. Okay? So now I'm not done. All right? So that's just my next one. I don't automatically go to pi over 4. It could happen that it will be that way for this particular problem. But, all right, we're going to calculate it just to make sure that we're right. So again, tangent has a period of pi. So I'm going to take for my new full period length, okay, so this is essentially my new starting point here. I want to find my new period length, so I take pi, okay, divided by 2. Well, if I want to figure out, okay, again, okay, how much equidistant step I had was, because remember we just break it into 4, so much like I did within my sine and cosine functions, I just multiply this by a quarter. All right? When I multiply this by a quarter, I get my new 1/8. All right? Or pi over 8, my bad. So pi over 8. So every new step is a pi over 8 away from negative pi over 4. Well, negative pi over 4, all right, is just going to be negative 2 pi over 8. So if I want to add plus 1 over 8 to that, so plus 1 pi over 8, okay, I'm mentally just going to be going to, that answer is going to be negative pi over 8. Add pi over 8 to that, 0. Add pi over 8, I get pi over 8. And remember, it's 4 chunks. So chunk 1, chunk 2, chunk 3. I need to make my 4th chunk. And just know that at the end of the 4th chunk is again going to be my new, my extra vertical asymptote. So that vertical asymptote, pi over 8 plus pi over 8, gives me that pi over 4. And that's my next vertical asymptote. So now what's going to come into play are these values. And these are the ones you kind of have to remember, which is kind of why your teacher stressed when you go around the unit circle, having to remember the sine ratios and the tangent ratios and what their outcomes were. And it's going to come down to at this point. So the original tangent function, all right, looked like this. So it was this value, this value, this value. So these values were 1 and negative 1. So 1, negative 1. And essentially what we're going to do, if you look here, okay, if I have a negative, all right, I'm just saying that I'm going to take these values here and multiply them by negative 1/2. So this was my original negative pi over 4. That's my, so original, then the next one. So the tangent function has a little pattern. It goes undefined, negative 1, 0, 1, undefined. Well, all I have to do, if I remember that pattern, I really only have to remember the in-between of negative 1, 0, 1, which is basically thinking about counting or looking at a number line, negative 1, 0, 1. I just multiply negative 1 by whatever this is. So negative 1 times negative 1/2 gives me positive 1/2. So there's 1, there's 1/2. I plot my point. 0 times that, 0. And then I also have the 1/2. So times here, so negative 1/2 times that gives me the negative 1/2. Okay? So now I have this pattern that kind of just flips. And it's very simple. So what you begin to notice is kind of like this kind of plays. It's not called amplitude, but it's the similar role to amplitude. So if you were to move this, so say you had a vertical shift of some sort, what you begin to notice is that this point, okay, is the displacement from wherever your new horizontal axis of this centering value is. So I just go up a half, go up a half. The negative, okay, the negative just flip-flops it. So the negative kind of just flips it back. So if it's positive, it has this one. So as I read it from left to right, my hand is going up in the positive direction. If it's negative, from left to right, my hand is going down in the negative direction as I increase. But again, the important part here to get back to is that we have to find our new starting point, and then we just simply take our tangent original period of pi, divided by the coefficient. So if this were 4, I would say pi over 4 here. Multiply it by a 4th. That gives me how much I'm adding to get to each new step. Just know the end step is your other vertical asymptote when it deals with tangent. And this value here tells me the point. If it's positive, I go up a half. If it's negative, I go down a half. If it's whatever that number is. If that was a 5, I would go up 5 and then down 5 here. If it were a negative 5, I'd go left, then up 5. If it were a negative 5, I'd go right and then down 5 this direction. So I hope that helps with the idea of what you were looking for tangent in general. you know, they can get a little bit more complicated when you start putting pluses and minuses, but I think I've already made this video longer than I kind of, or maybe you would like it to be. But I hope that kind of helps with the idea of vertical asymptotes, where they come from. And if you have any other questions, let me know, and I'll see what I can do.